Hello and welcome to this ninth lecture of this module, and you know that this module we are discussing about multiple random variables. Currently we are discussing, and we started our discussion from the last lecture, that is functions of multiple random variables. In the last lecture we have given the indication that what all the different functions could be. Particularly the first step that we are doing is that one function of two random variables, and there are several functions is possible. Last class we have seen that summation of two random variable, what is their properties and all we have discussed. We will start today's class with a problem on that, and then we will gradually take up some other type of functions of two random variables, and we will see, and in the next class we will go for the two functions of two random variables. So our basically today's lecture is a continuation of our last lecture. There is a function of multiple random variables, and basically we will be continuing the same thing again for the next lecture, where we will discuss about the two functions. So up to today's lecture, it is a one function of two random variables, or two, or sometimes it is sometimes we are taking the more also. So first we will what we have done in the last class is the general discussion on this sum and difference of two random variables. So here we will specifically take up a specific case where the random variables are normal distribution, is having the normal distribution. So how? The question is, if there are two normal distribution, then if we add them, or if we take a difference between them, then the resulting function is follows what distribution, that we will see first. And after that we will take the maximum of two or even more than two random variables, and then minimum of two or more random variables, product of two random variables, that is if x and y is there, so what should be the distribution for x, y, and for the quotient of two random variables, that is x by y. So these things we will see along with their application, some problems from the civil engineering for different specific case that we will see for each and every of type of this function. So this may not be the end for so the type of function that we can consider out of two random variables, this may not be the complete list. There could be the other functions as well, where I can take this summation of the square, for example, x square plus x square plus y square. So that type of case also can be that their functions, their properties of their that type of function can also be estimated. But the basic thing what I feel is that the basic idea, if it is clear from whatever being taken up for the discussion, if that basic concept is clear, then any type of functions can be handled. So that what we will try through these few examples, we will just try to develop the concept, so that this can be easily extended for the other type of functions as well. So the first we will take the same thing again that we have discussed, but it was discussed in the general concept for any type of function. Here we are taking the specific case of the normal distribution, because this type of situation is very common, particularly in the civil engineering application, that when we are adding the random variables, and I can assume that those random variables follows a normal distribution. So we will just see that in case of two random variables, what is the property of their summation and their difference, and then we will try to generalize that thing from the two to more number of random variables. So here that if x and y are independent normal variates, that is, it is having the normal distribution for their and their parameters are mu x and mu y, and standard deviations are sigma x and sigma y respectively, then the function, if we express it as that z is equals to x plus y. So we are taking the summation of two random variables which are normally distributed, having their own mean and standard deviation. For x it is mu x sigma x, and for y it is mu y sigma y. So also we have the PDF of two statistically independent random variables x and y. This particular thing we discussed in the last class, that is, if two random variables are independent, then then the distribution of their summation is that if that is z, then this fz can be expressed as the integration over the entire support express in terms of any one of the random variables. Here it is expressed in terms of the y. So, this one is a z minus y, because you know that this x can be expressed by that z minus y from here, and f y y, and that we are indicating with respect to the y. So, if we put this one that we discussed in the last class in this expression, if we put their form, that is that normal distribution form, that also we know what is a normal distribution form, and then we can see that this can be expressed in terms of this, that is that 2 pi sigma x and that 2 pi sigma y, this can be taken out as a common, that is, so it comes at 2 pi sigma x sigma y, and then we are taking the integration over the entire support of this random variable y, that is minus infinity to plus infinity, and that that exponential of, so this the first component, it comes from that random variable x. So, how it comes, that we are just replacing this z minus y in the place of the x. So, this is basically x minus mu x by sigma x whole square that we know. So, that was replaced, that x is replaced by z minus y, and also for the y we do not have to make any change, because we are taking it to the random variable y. So, so it is y minus mu x by sigma y whole square. So, this expression, if we do this integration, then we can see that we can take out some of the constant term. So, this mu y sigma y and this z minus mu x sigma mu x by sigma x whole square. So, this component we can take out from this integration term, and the remaining that minus infinity to plus infinity exponential of 1 by 2 minus and a y square minus 2 b y dy. Now, this a and b are two constants in terms that can be expressed in terms of the that z, which are apart from the apart from y, the other variables can be used to express this a and b, and which is here it is expressed. The a is equals to 1 by sigma x square and plus 1 by sigma y square. So, this square should be on the top, you know that this is a variance that we are referring to. So, this one, and b is equals to that z minus mu x by sigma x square plus mu y by sigma y square. So, these are the constants, that a and b, and now this for this integration, if we just do some substitution, like w is equals to 1 minus b by a, and if we do this integration, we will finally we will get this form, that is square root of 2 pi by a exponential b square by 2a. So, this expression now if we put in place of this integration, that is here, then what is the form we will get, total form for this distribution of this f z, that is our interest. So, here it is that so we are just placing this form in place of this integration, and after some algebraic arrangement, rearrangement of this full expression, we can arrange it in this form, and which even further can be rearranged in this final form, which is that 1 by square root of 2 pi in bracket sigma x square plus sigma y square exponential of minus half z minus mu x plus mu y divided by square root of sigma x square plus sigma y square whole square. Now, if we see this form, that is for the function z, which is the summation of x and y. So, this form is also one normal distribution with some different parameter. What are those parameters? So, this is the mean, which is now the summation of the individual means of this x and y, and this is the standard deviation, which is the sigma x square plus sigma y square square root. So, if we take this one, of course, this will be the square root of 2 pi, and this part will be outside of the square root, or there will be a square. You know that this is a normal distribution form. This is coming from this is the form of this random variable z. So, the sum of two independent Gaussian random variables is also a normal density function, but this normal density function having the parameters are, as we have just now seen, that mu z of this resulting function is equals to mu x plus mu y, and sigma z square is equals to the summation of their individual variance. This can be now, this is very interesting that when there we are taking the two normal distribution, we are adding them up, then the resulting variable is also normal, also a normal distribution having their mean is the summation of their individual means and the variance is the summation of their individual variance. Similarly, we can also do the same exercise to know what is the distribution if we take the difference, means that x minus y, if we take what is the distribution of this function, their difference. So if we do the same exercise, it will come as that the difference also will be having a Gaussian random variable, and their parameters, that is the mean and variance, will be, the first we take the mean will be the difference of their individual means. So here you remember that the function that we have taken, it is the x minus y, that's why it is mu x minus mu y. If we take the function as the y minus x, then it could have been mu y by mu y minus mu x. But if you see the variance is not the difference. In case of the difference in the random variable as well, it will be always be additive. Okay, so in case of the difference also, the variance will be the summation of the their individual variances. So irrespective of whether it is x minus y or y minus x or even x plus y, for all these cases the variance will be the same, that is the summation of the individual variance, but this mean will be changing as per the function is. So now these things, as you can see that here we have taken the two random variables. Now this can be easily extended for the more than two random variables. So if we take, say that n numbers of random variable, all are independent and that their distribution is normal with their individual means and variances, then the resulting function, if I take their summation, then the resulting function will also be a Gaussian distribution having their mean is equals to their summation of their individual means, and the variance is the summation of their individual variance. This is what is explained here. That is, if we just want to generalize it, that is, a z is equals to even that we can even multiply with a constant, that is ai xi. So each random variable is multiplied with a constant, that is ai. So these are statistically independent normal variates with mean and standard deviation as mu xi and sigma xi respectively, and ai's are constants. So in that case, that z will also follow a Gaussian distribution with mean and variance, as the mean will be the summation of their individual means. Now you know that if we just multiply with a scalar component to a normal distribution, their mean can be just multiplication of their with their constant, that we have seen when we were discussing that expectation. So here, so that mean also will be, that is a summation of that ai mu xi for I varies from 1 to n for all the random variables concerned, and the variance will be that ai square. So this also we explained when we are taking that second moment, that is variance of the random variable when it is multiplied by a constant, that constant should be squared in case of the variance. This we also discussed earlier. So in this case now, if there are n summation of this n such random variables, their variance will be the summation of that ai square sigma xi square for I varies from 1 to n. So if we take one example now on this the summation of where all are normal distribution, we have taken a structural safety problem. For the safety of a building, the total force acting on the columns of the building should be examined. The total force acting on the columns are the effects of the dead load, live load and wheel load. There are other loads as well, but here we have taken three different types of load. These are the primary and most important load, and there are different combinations we generally consider for this. So if the load effects acting on the individual columns are statistically independent and normally distributed with their respective mean and standard deviation, as this, for the dead load the mean is 22 kilonewton and its standard deviation is 1.5. For the live load the mean is 30 kilonewton and this their standard deviation is 3.5, and for the wind load it is 18 kilonewton, and that their standard deviation is 3 kilonewton. So, if this is the situation of the loading system, then we have to determine the mean and standard deviation of the load acting on the column. So, it is the total load. So, we have to take the combination of this all these three loads. Here we can just take for the simplicity's sake, we can just add them individually, we can add them and find out what is the distribution. But you know that sometimes due to the factor of safety, we have to multiply this force with some constant. So, those are separate issues, but you know that if there are some constant is multiplied also, then the last thing that we have discussed, that AI is the constant that is multiplied with the individual random variable, that also we can do. But here what we are looking for is that just the simple summation of the all three forces, what is their distribution, that's what is asked for. Now, the second question is that the strength of the column also follow a normal distribution with a mean equals to the 1.5 times of the total mean force, and the coefficient of variation of the strength is 15%, and the strength and the load effects are statistically independent. Determine the probability of the failure of the column. Now, to give a little bit background of this, the word the strength that is being used here for the column is that how much force it can resist. Okay. So, that is also is having the same as that your loading unit. So, that now what to determine the failure or to declare that this is failed, what we can say is that if the difference is becoming negative, that is if the load is exceeding what is the strength of the column, that time we are calling that this column is failed. So, you can see that the first problem basically we have to go for a summation, and the second problem we have to go to a difference between the strength and the total load on the column. Okay. So, to solve the first part, the total load be present, if it is represented as the T, then this T is equals to that D plus L plus W. Now, as I was telling that there could be some factor or the margin factor or factor of safety that we can multiply with this individual loading system, and that need not be same for all the loading pattern. Okay. So, depending on that this final answer may change, but here if we just consider the total load is the dead load plus live load plus wind load, then it follows then we know that if all these three are the normal distribution, then it follows a normal distribution as well. So, this mu of this T, that is total load, its mean will be the summation of their individual means, that is which is 70 kilonewton, and its standard deviation is nothing but the positive square root of their summation of their individual variances. Now, this 1.5 square, which is the standard deviation for the dead load. So, 1.5 square, 3.5 square and 3 square, and after that we are taking the positive square root, which is the 4.85. So, the total load is also a normal distribution having its mean is 70 kilonewton and standard deviation is 4.85 kilonewton. Now, that failure of the column, so let the strength of the column be represented at S, and if the strength of the column S is less than the total load T. So, here now from this to calculate the failure, we have to consider the total load. So, if it is less than the total load, then the column will fail, and if the R represents the difference between the strength and the total load. So, we are just introducing a new random variable which is R, and which is the difference between that S minus T. Now, it can be easily seen from this expression that if S is less than T, that time obviously the column will fail. So, that time R will become negative. So, if then the failure is represented as R less than 0. So, R follows a normal distribution, therefore, we know that as S and T both are normal distributions. So, it should be the mean of this R will be that mean difference of this their means, that is mean of the strength and mean of this total load, and mean of this one as expressed is the 1.5 times of the total load. So, 1.5 multiplied by 70, that is the mean for the strength, and minus mean of the total load is 70, that what we have seen just in the previous part of the problem. So, that difference is 37.5 kilonewton. So, the R is having a mean of this value, and we have to see its standard deviation as well. So, the standard deviation is that so we have to find out what is the standard deviation of the strength first, and standard deviation of strength, it is the coefficient of variation that that was given, that CV was given as 15%. So, now this 15% multiplied by 1.5 multiplied by their mean, so it will give you the standard deviation of the strength, and that square, so variance plus the variance of the total load, which is 4.85 square. So, if we take this one, so the variance comes as 16.4798 kilonewton, this one. So, this would be the kilonewton as so that R is also, so the difference of their strength and total load is also a normal distribution having its mean 37.5 kilonewton and standard deviation is 16.4798 kilonewton. Now, if we want to know the probability of the failure, so probability of the failure is equals to probability of we have denoted it as R. So, R less than equals to 0. So, R less than 0 of course here to declare it to be the failed. So, which is equals to, now that we have to reduce, get the reduced variate, that is the so this is the value that x minus, or the R minus, R is a 0. So, 0 minus mu R divided by sigma R. So, this is the mu R what is, so this will be R, this is not x. So, mu R what we have calculated is it's 37.5. So, minus 37.5 divided by standard deviation, which is 16.4798. So, it is the phi of minus 2.2755. So, this now we can get it from the standard normal distribution table, that that in the earlier classes we have discussed how to refer to that standard normal distribution table, and from there we can get its value at the probability. So, now, so it can also be written that 1 minus phi of 2.2755 due to the symmetry of this standard normal distribution curve, and this value is 0.98855, which is giving you the probability of the failure of the column is 0.01145. Now, to get this one, that we have to refer to the standard normal distribution, and for this 2.275, so it was 2.2755 will be that this is 2.27 is this and 2.28 is this. So, you have to get an interpolation between these two values, which is 0.984 or 98845. So, what is this value? That 98855, that value we got as the interpolation between these two extremes, that is 2.227 and 2.28. This will be 2.275, as we have seen that what we are referring to here, 2.275. Well, so our next discussion is on this maximum and minimum of two or more random variables. So, if sometimes this is also important, is that we have the several random variables, or we are interested to know what is that what is the maximum of the individual random variable. Suppose that we know that, suppose at a place the earthquake intensities we know, and what is the maximum intensity of individual earthquake is having some so we are interested to know that in what should be the maximum intensity, what is the properties of the maximum intensity. So, in a particular stretch of period, if we are interested to know that this many events has occurred, so this many events are likely to occur, then what is the distribution of its maximum intensity of the earthquake, like that. Similarly, suppose that we are just picking up the annual maximum flows. So, we are taking that the maximum flows from each month and what is their distribution, and we want to know that out of this n years what is the maximum flow that can occur, or similarly what is the minimum flow that can occur. Sometimes that is also important for some management purpose. So, to address that type of questions, we need to know the distribution of the maximum of two or more variables. So let that x1, x2, x3 up to xn are the n variables, and these are defined, and the function which we have defined as a y is equals to maximum of this n variables, the maximum of x1, x2 up to xn. So now if we want to know what is the CDF of the y, then CDF of the y is that y less than equals to the specific value y is equals to that it should be, so that x1 is also less than equals to y, then x2 is also less than equals to y, like that all the random variables should be less than equals to y, which is nothing but the joint CDF of all these random variables x1 to xn for their for the specific value y for which we are looking for the CDF. So if this now the one more assumption, if we put that if this x1, x2 are independent to each other, then their joint distribution can be expressed as the product of their individual marginals. So now, so this is the marginals of this distribution, and so that we can this sign is for the multiplication of individual CDF, okay, for the xi. So I varies from the 1 to n, that is it is the product of all product of the marginal CDF for all the random variables. Now again one more assumption, if we just say that all the distribution of all of them are similar, that is fx1 in terms expressed in terms of y, fx2 expressed in terms of y, all this the distribution of all these random variables x1, x2 up to xn are having a similar distribution, which is can be written as a fx y, then these n variables have the same probability distribution. So if that is the case, then fy, so the product will be just their power to the n. So you see that here to reach from this expression what we have started with, so this expression, this CDF, from this original expression if we want to go to this expression, that is it is the product of the say fx y power n, there are two assumptions involved. One is that they are independent and identically distributed. If that is the case, then we can say that this fyy is equals to fx expressed in terms of y, of course, power n. Now if we want to know what is its PDF, that is we have to do the differentiation with respect to y, and this is the final form, that is n fx expressed in terms of y power n minus 1, and this differentiation you know that is their PDF, that is fx of x, that is PDF of their individual random variable expressed in terms of y. And similarly, if we take that that minimum of two or more random variables, that is when we are talking that this z is equals to their minimum of x1, x2 and up to xn, and if that x1, x2, xn are independent to each other, then this fz is equals to 1 minus of this product of their this probability, that is xi greater than z. So we have taken that 1 minus. So now this one can be expressed at 1 minus the product of their 1 minus their CDF of the individual random variables. Now considering that these n variables have the same probability distribution, that is if they are having the identical distribution, then this product can be replaced as a power of n to this one. So that this is their what is their identical distribution, that is fx for all the individual random variables x1, x2 up to xn. So this one what we can write, so finally what we can write, that this CDF of the function z, which is the minimum of all these random variable xi, is equals to 1 minus fx expressed in terms of z power n. Now if we differentiate this one to get the PDF of z is equals to, we have to differentiate with respect to z this function, which is n multiplied n times of this 1 minus fx expressed in terms of z power n minus 1 and multiplied by their fz of z. So this is the expression that we have seen is for the when we are interested to know the minimum of n random variables. So, which is n multiplied by 1 minus fx expressed in terms of z power n minus 1 fx PDF expressed in terms of z. And if we are interested to know what is their what is the distribution of their maximum one, the maximum of the n random variables, then that expression is that n times of their CDF fx expressed in terms of y power n minus 1 multiplied by their PDF expressed in terms of y. So, now if we take one problem based on this one, suppose this is the problem on the peak flow. So, there are different flood events occurs, and we want to know. So, to characterize a flood, there are different attributes can be considered. One is the duration of the flood, total volume of the flood, peak flow of the flood. So, there are different characteristics. So, in this example, we have taken the peak flow, and here what we are interested, we know that what is the distribution of the peak flow. Now, if there are certain numbers of flood occurs, and to prevent that, to do a proper flood management, we want to know what is the maximum peak flow that can occur for different design purposes. So, that type of problem is taken here. The PDF of the peak flow of the flood events at a gauging station is exponentially distributed as follows. So, fx x lambda e power minus lambda x, where x is greater than or equal to 0 with the lambda parameter as 0.3. Now, if there are so n flood events, so here we have taken the 5 flood events. If the 5 floods are observed in a year, determine the probability distribution of the maximum peak flow of the flood occurrences. So, so here what is that intuitive is that those assumptions that we have discussed about during the theory. So, for all the floods, it is having the same distribution. So, all the floods means in case of all the floods, their distribution of their peak flow are similar, and obviously that for this one, for the one flood to another flood, that their distributions are also independent. So, these two assumptions are there when we are declaring that that the distribution, that PDF of the peak flow of the flood events at that gauging station is having this distribution with the lambda parameter is this. So, so there are 5 such flood events. What is the probability distribution for the maximum peak flow out of these 5 flood events? So, to solve this one, as we are interested to know their the maximum intensity, that maximum of the peak flows, then this is their PDF that is given, that is lambda e power minus lambda x, and this is an exponential distribution, and you know that if for the CDF of the exponential distribution is 1 minus e power lambda x. So, here we are expressing in terms of the y, as we have just keep a parity with the theory. So, this is expressed in terms of the y, and which is the CDF of the individual peak flows for the different floods. Now, if we assume that the peak flows of the flood occurrences are independent from each other, then we get that this Fy, that is y is the now the maximum of that 5 maximum peak flow out of these 5 flood occurrences. Then this Fy should be the multiplication of their individual CDF. So fx expressed in terms of y power n. So, 1 minus e power minus 0.3 y power 5. So, where this y is obviously greater than 0, greater than or equal to 0. So, now by differentiating we obtain the PDF of this maximum peak flow as this Fy y is equals to n fx y power n minus 1 of their individual PDF. So, this is now n is equals to 5, fx y is that CDF is 1 minus e power lambda e power minus lambda y. So, which is lambda is 0.3. So, this is replaced by this one and expressed in terms of y power n minus 1, which is 4, and this distribution, this PDF is 0.3 e power minus 0.3y, that is lambda e power minus lambda y. So by expressing this on 1.5, 1 minus e power minus 0.3y power 4 e power minus 0.3y for y greater than or equal to 0. So this is the distribution for the maximum peak flow. Now if we are also want to know what is the minimum of this peak flow, then this expression we can refer to, that is fz z equals to 1 minus of 1 minus fz power this one. So this expression we have discussed earlier, which is then 1 minus this is now e power minus 0.3y power 5, and this is can be expressed also 1 minus e power minus 0.5 y. So why this is has been discussed here is that just to give a special note that when we are interested for the exponential distribution, if the individual random variables are distributed exponentially, then if we are interested to know what is their maximum out of this n individual random variables, then we have seen what is their expression. But if we are interested to know what is their minimum of the different random variable, in case of the exponential, I am just specifically talking, so that also will have the similar form of this distribution, that also will be the exponential distribution, which you can see it from here also. That is, if we are talking about the minimum one, and if this is the expression, if we just put, which is coming as 1 minus e power minus 1.5y. So this is the form of the exponential distribution with obviously some different lambda parameter. So the note is that it follows the same distribution of the peak flood flow x in case of the minimum only, but not for the maximum. Okay, so other two things, the other two type of variables, type of the function is that one is the product that we will discuss, another one is the quotient that we will discuss, and with reference to their some that integration area and all, so that this concept. So last time, yesterday in the previous class also we have explained that how we should take the integration limit in case of, we have discussed is for the summation and difference, so x plus y and x minus y, on what area and what should be the integration limits that we have discussed. So here also we will take up similarly. The first one is that xy, and other one is x by y. So first we will take the product of two random variables. Let that x and y be two random variables, and the probability distribution of z is equals to xy has to be determined. The probability distribution of z equals to xy is determined by integrating the joint PDF of x and y for those values of the product x, y that are less than or equal to z. So this fz expressed in terms of this z is equals to the probability of z less than that specific values. If we want to know this one, then we have to integrate that joint distribution of this x and y for the area where the product of x, y is less than z. So this is the basic equation that you know, which we are interested to know that what is the CDF of the z. Now properly we have to identify that on what area this integration should be done for which variable. So if you now take this one, that is first that we are discussing that z equals to x, z equals to xy. So there are two possibilities are there. One is that, so this is the line where if we just take a specific value of z, then these are the lines where this y is equals to z by x, and this is one and this is another. This is the first quadrant, this is the third quadrant. So and these are going to this infinity, plus infinity, this is also going to the plus infinity, this is going to the minus infinity, and this is coming to the minus infinity. So if this is this shaded area is that xy less than z. So now this, when we are talking about the xy less than or equals to z, and we have shown this one, this shaded area. Now, depending on the what is the support of this individual random variable x and y, this area, whether we will include this coordinate or not, that is the separate issue. But this should be obviously be bounded by these two curves. So, in this first quadrant, this is the curve, and in the third quadrant, this is the curve. So, if we want to now integrate it, now we can easily see that we have to do the integration in two different parts. One is that for this, if I just take this is a y, this is that with respect to this axis. So, one is that we have to take it from this side, and other one we have to take it from this side. Now, if we want to do this integration now, and if we are taking the small strip that we have discussed in the previous class also, that if we take a small strip from here to this say infinity, depending on the case whether this area will be included or not, that is the separate one, but it should be lower bounded by here. It should be lower bounded, but for this side this will be upper bounded. These two are the thing that we have to consider here. So, now if we want to do this find out their integration limits, then you see that for this fz, that the expression that we have explained is, first what we are taking is that for this z by x, for the y, for that y we are taking first. So, this is now we are for the left hand side, that means in this area. So, this is now the lower bounded by this z by x. So, y is equals to z by x, and going up to plus infinity. This is also a general term, whether it will go to the plus infinity or it should be bounded by bounded at 0. That depends on this what is the range of that particular random variable. So, this is the thing. So, that strip if we take, and after that for the x axis, the integration limit is minus infinity to 0. So, minus infinity to 0 means it is going to this minus infinity, and we are doing it in the two parts. So, first we are coming up to this axis, so which is that x equals to 0. Now, for the right hand side, if we want to express for the other expression, which is we are taking the first for this with respect to the y, and this should be the upper bounded now, which is the upper bound is that z by x. So, this upper bound means here. So, from this minus infinity it will go to that upper bound. Now, again the similar point, whether this area will be included or not, or the lower limit will be 0 to that z by x, or from the minus infinity to the z by x, that depends on the individual random variable. So, and after that when we are taking that limit for the x, so this limit for the x will be from this axis, that is from y axis, that is x equals to 0 to the plus infinity. So, you see here the limit is from the 0 to infinity. So, the first one, for in case so far as the x axis is concerned, we are taking it from the minus infinity to 0, and for the other for the positive x axis we are taking from the 0 to infinity, and similarly this inner limit, that is for the y, is also changing accordingly. So, now there are some certain substitution. If that t is equals to x y, then if we want to just express in terms of this t, and this integration if we do, and finally we get the total that final form as that from minus infinity to z, and then integration from minus infinity to plus infinity 1 by mod x f x y, that is a joint distribution expressed in terms of x, and t by x with respect to that x, integration with respect to x, and final integration with respect to that t, so that it will be expressed in terms of z only to get there what is the distribution function for the random variable z, which is actually equals to x y, that is product of x and y. So, differentiating now again, so this is a CDF. So, differentiating the above equation with respect to the z, we get as it's given here. So, if we just do this differentiation to get its PDF, so we will get the final form as this 1 by mod y f x y z by y with respect to y, or we can also do it with respect to the x, that is 1 by mod x fxy, x by z by y, z by x with respect to x. So, depending on the which variable you are just substituting, depending on that you are getting what is its form of this PDF. Now, if the x and y are independent, then the product of their marginals can be substituted from their bivariate PDF, and thus we get that. This joint actually, if you know that if it is independent, then this joint can be expressed as the product of their individual marginals. So, this expression we have just taken that with respect to the x. So, this expression can be expressed in terms of this fx of z by y and fy of y with respect to y, and similarly also this can be also expressed in terms of the x as well, and that is fx of x and fy of z by x with respect to dx, and 1 by mod x from minus infinity to plus infinity. Both the expressions are possible. Now, similar to the product of two random variables, using the same principle, the quotient also can be found out. So, to find out the quotient, that is fz of z, that is z is less than equals to this z, which we can write that x by y is less than z and y greater than 0. So, this range we have to consider, and plus the probability of x by z for the case when y is less than equals to y is less than 0. So, this can be expressed that x is less than equals to yz, y is greater than 0. So, two different cases, two different areas again. One is that y greater than 0, other one is the y less than 0. So, this can be expressed that xy less than z. No, this is that there is that x by y less than z. This is wrong. So, x by y less than z for the joint distribution, that integration if we do. Similarly, again you can just express this x by y, or that x equals to that yz, that expression if you just take, and that limit if you consider, then the integration limit in case of the y, if you take the strip along the y, then this integration limit will be from yz to the plus infinity, that is x equals to yz, because our function is z equals to x by y. So, from the for the lower limit for the y will be yz to plus infinity, and for the x it will be minus infinity to 0 first, when we are considering that y the one zone, that is out of this there are two separate zones. So, it is for the negative side of the x axis, that is from minus infinity to 0, and the other one is for the positive side of the x axis from this 0 to infinity, and this limit will be from the minus infinity to yz of this limit, and these two integration if we do, we get that CDF of z. Now, the PDF of the quotient, that is w is equals to x by y of two random variables x and y given as. So, finally, we are getting that minus infinity to 0 mod y f x y, that is joint distribution expressed in terms of w y comma y dy, plus for this 0 to plus infinity mod y joint distribution expressed in terms of w y and y, and we are getting the final from this minus infinity to the plus infinity mod of y joint distribution expressed in terms of w y and y dy. Similarly, this expression can also be expressed, as you know, in terms of the x in terms of the x also. There the accordingly you have to change the substitution, which one you want is that this y should be substituted and it should be expressed in terms of the x, and then the integration should be taken with respect to x. Now, again if the x and y are independent to each other, then we can say that this joint distribution of this of their quotient is equals to this minus infinity to plus infinity mod of y. Now, this joint distribution is basically expressed in terms of their product of their individual marginals. So, this is the marginal of this x expressed in terms of wy, and this is the marginal of y expressed in terms of y, and doing the integration with respect to y. And similarly, also you can express the same thing with respect to the x as well by proper substitution. So, instead of y, there will be express it in terms of the x first, and then we will do the integration with respect to x. Here one example is shown. Suppose that there are two random variables. One is that product of z and the quotient is w here, that is so they are individual. So, these are the two random variables is considered where both the random variables are uniform. So, this dotted line, as you can see here, this is the uniform distribution for both the random variables, and it is uniform between 0 and 1. Now, if we want to know what is the distribution of their product, and this product is say z, then this line that you can say, this is their PDF for their product, okay, and this line that you can see, this is their PDF for their quotient, okay. So, this can be directly can be obtained from the expression just now, which we have explained just now. So, and now, so if we just want to generalize the same thing, that the product and the quotient of statistically independent log normal variate is also a log normal. So, here we are taking a specific distribution again, that we are specifying that all this normal all these random variables are log normally distributed with their and their product, as we are writing that this is z. Z is the multiplication of this all these random variable from this x1, x2 up to xn, and this xi is the statistically independent log normal random variables with parameter lambda xi and sigma xi. Lambda xi is basically their mean, that is the log of that z is equals to the product of their log of their all the random variables. If we take that product, then as these xi's are normal, this z is also will be normal with the mean and variance as shown below. This is if they are normal, because we have taken the log. So, once you take the log of the log normal distribution, then it becomes normal, that you know we have discussed earlier. So, this now the final parameter, that is lambda z is equals to expectation of log log natural of z, which is a summation of their individual means, that parameter, the lambda xi, and this is the standard deviation of that they are individual variances. So, this is the summation. No, this will be square. This will be square, the sigma z square. Otherwise, you have to take the positive square root for both this expression. So, hence this z is also a log normal distribution with the above parameters, that is lambda z and sigma z. Mean, this lambda z is the parameter when it is the mean of this log transformed random variables, and this is their standard deviation. This is the standard deviation of the log transformed random variables. One small example we will take: the settlement of a footing on the sand may be estimated on the basis of the theory of elasticity as follows: S is equals to P bi by m, where S is the footing settlement in meter, P is the average applied bearing pressure in tons per square meter, and B is the smallest footing dimension in meter. I is the influence factor depending on the footing geometry, depth of amendment. Depth of amendment means how deep it is from the surface, depth to the hard stratum. This m is the modulus of compressibility. Let P, B, I, M are independent log normal variates with parameter lambda P, lambda B, lambda I, and lambda M, and their and this sigma P, sigma B, sigma I, and sigma M respectively. The values of the mean and coefficient of variation used for the design is shown in this next slide, which is here. That is this is the mean and the coefficient of variation for individual these parameters. So, determine the mean settlement of the footing and its coefficient of variation. If the maximum allowable settlement is 15 centimeter, what is the reliability against the excessive settlement? There is the probability of no settlement. So, as we have seen for this log normal variates, that is this sigma SS square, which is the both, it is considering both, that is so sigma SS square is equals to the summation of the individual squares. So, this 0.0454. lambda p is equals to by from this expression we will get that minus 0.00405. Similarly, lambda b and lambda I and lambda m, all these parameters we will get, and then so the for that resulting random variable which is s, it should be the summation of all those lambda parameters. So, this is these are the lambda parameters for the individual random variables. So, this is the lambda for the final random variable which is s, and the mu of this means settlement of the for footing, as we know from this log normal distribution, is from this expression we just replace this lambda and sigma s this. So, this will be the mean settlement will be 0.092 meter, and the coefficient of variation which is approximately equal to the sigma s and which is 0.2131. If these two parameters we get, then the reliability that what we are expressing, that it should be the settlement should be less than 6.5 centimeter, then the reliability. So, we can just find out the reduced variate by taking the log of their this 0.15 by 100 this much meter. So, this is 0.15. I think in the problem it was asked for the 15 centimeter, right. So, this is 15 centimeter. So, this will be 1.5 centimeter. So, if we just take this one, this is the correction 1.5 centimeter. So, this log of this one minus their mean divided by the standard deviation, we get the 2.31, and which is equals to that 0.9895, which we can get easily from the cumulative standard normal distribution table. So, the reliability is equals to 0.9895 for the problem that we have discussed. So, in this class on including the last class, both the classes we have taken two functions of the multiple random variable. Particularly, we have discussed one function from two random variables, and in the next class we will continue and we will take up the two functions of two random variables. So, means what are the joint distribution of those two resulting random variable, that we will be discussing in the next class. Thank you.